Hi there, this is Math 145, Section 8.1, and here we're going to expand on what we learned of Chapter 7 with that normal distribution stuff, and basically have yet another application where we have this variable that is normally distributed, and we're going to answer questions like, what's the probability that such and such blah 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 is more than 30 or less than 25 or between 25 and 30 or something like that, right? And we're going to be able to use the normal distribution stuff we learned in Chapter 7 and to a lesser extent the empirical rule stuff that you may very well see from time to time, okay? So let's look at the title. It's called Distribution of the Sample Mean. We're going to find the sample means, as we'll call them, are normally distributed. Now, think about this thought bubble. Take 20 samples and find the means of each of those 20 samples, right? Maybe we ask 100 people what their income is, right? And think about this. You ask those 100 people what their income is. Okay, great. You can find the mean of that data. But what if you asked another 100 people? They'd have a different mean, wouldn't they? And they ask another 100 people, they'd have a different mean. Well, it turns out that the means of these samples are normally distributed. The means of the possible samples are actually normally distributed. So I can ask questions like, when I survey 100 people about their income, what's the probability that the mean income of my sample is more than $100,000 or something like that? Won't that be fun? All right, let's look at another example here. It's a very cool example that we have here. Please look at that. Pause me down, of course, read that over, and then we'll go on with some definitions and more, of course, examples together. All right, so what we've got here with this example is a discussion of a very important survey that the U.S. government undertakes. So here's the idea. They are going to randomly sample 250,000 households and ask them various questions. And the one question we're kind of focusing on here is they asked, what's your income? And then for the whole sample, they found the mean income, right? And so in 2013, from one of their samples, they got the mean income of $72,641. Now, you can imagine that another 250,000 households would have given different answers and so would have a different mean. But this is where the cool thing comes in here. That sample is randomly selected, right? So doesn't that mean their sample mean is a random variable? And if it's a continuous random variable, then we can do with the sample means what we did back in Chapter 7 and answer those wonderful probability questions. So we are going to see the distribution of the sample mean. Essentially, we're going to be told that the sample mean is normal under most circumstances. There will be some exceptions to that. If the sample mean is determined not to be normal, then we cannot use our Chapter 7 stuff, and we really just can't answer the question at this point. But there's other statistics that we would maybe learn later that would help us deal with those questions. We're going to investigate, as we always do with different variables, the distribution as in its shape, center, and spread. So we're going to actually have formulas, essentially, for the mean and the standard deviation of the sample means. All right, so these definitions here are sort of important and sort of not. For the technical, here's a definition, it's not really that useful. But why they're really here is to show us the notation and to make sure we're kind of aware of all that notation and what that means. So first off, definition, The sampling distribution of a statistic is a probability distribution for all possible values of the statistic computed from a sample of size n. Now, again, the important part there is that n is the size of the samples that we might be talking about. And in each one of these problems, you will be told what the sample size is. That is a very important part of discovering what to do next in the problems. So that's important. Remember that a probability distribution is no more complicated than simply the list of the possible outcomes and their probabilities. So in the case of a continuous variable, you usually see that as an equation, and we're really thinking about it more as the area underneath this curve. Now, let's go to this next definition here, and again, we just talk about the sampling distribution of the sample mean, so we're just getting a little bit more exact. This is the probability distribution for the sample mean that we're going to be talking about, and again, really, we have it here for the notation. Okay, so X bar we know to be the sample mean notation. So it says the sampling distribution of the sample mean, X bar, is the probability distribution for all possible values of the random variable X bar. And again, we're seeing the sample means as a random variable itself. Computed from, I'm reading again, from a sample of size n. Again, we're just trying to note that n is the sample size. And then it says from a population with mean mu and standard deviation sigma. So again, we are really here trying to denote that the population will have a mean, we will call it mu. It will have a standard deviation, we will call that sigma. We will sample a certain number of items from the population. That number is n. When we find the mean of those numbers in my sample, that is X bar. So let's jump right in there with number one. Number one, it says the weights of pennies minted after 1982 are approximately normally distributed with a mean of 2.46 and a standard deviation of 0.02. So again, they're telling me my mu and my sigma from a population. Now, if this problem was back in chapter 7, we'd have stopped with that paragraph, and then we'd simply be asking something like, if I randomly select a penny minted after 1982, what's the probability that it's bigger or weighs more than 2.5 grams or something like that, right? Okay, now that was a chapter 7 problem. Here we're doing chapter 8. So we're not going to talk about randomly selecting individual pennies. We're going to talk about taking samples, this case of size 20, and looking at the results from those. In fact, the sample means. So now I want you to picture I took a sample of size 20 of these pennies. I found their mean, right? I did that many, many times, meaning, in fact, the book did this for us, luckily. They took 200 samples of size 20, right? They found the mean of every one of those size 20 samples. And it turned out, here's their data. This is the sample means of 200 random samples, all of size 20, right? So an awful lot of those means were right there in the middle. As you get further from the mean this way and that way, you get less and less samples that resulted in those means, right? The question here at the very end is, would you consider this skewed or symmetric? Does it look normal? It definitely looks normal. And again, the point here is simply that X bar is normally distributed. And so I'm going to be able to answer questions like, if I sample 20 pennies, then what's the probability that the mean of my sample is more than 2.5 grams? All right? A little bit different, but of course related to what we did in Chapter 7. Let's go on with more examples and, of course, lots more details. All right, so we do have these facts, very important here. The shape of the sampling distribution of X bar is normal. Now it does start off, if a random variable X is normally distributed. Then it says the sampling distribution of X bar is normally distributed as well. What that means is if the population is normal, then X bar will be normal too. Now, that's good, because if we know a population is normal, then if I ask questions about the X bar, I can answer them with my normal distribution stuff, right? But remember, back when we were doing all that Chapter 7 stuff, it was important that you knew what the mean and the standard deviation of your distribution was, because that played into how to find those probabilities, right? And so, of course, we have little formulas, little ones, not too bad, for the mean and standard deviation of the sampling distribution X bar. So we're going to start off, we're going to define mu and sigma from the population. That's what that first sentence is doing. Suppose that a simple random sample of size n is drawn from a population with mean mu and standard deviation sigma. And again, it's population mean, population standard deviation. And you'll again see how they're talking about n, the sample size. It goes on. It says the sampling distribution of X bar has a mean. Now notice what it's writing there. Mu sub X bar, meaning the mean of X bar happens to be equal to the population mean. No calculation needed there at all. It goes on, and standard deviation, so they're talking about sigma sub X bar, meaning sigma of X bar, that's going to be equal to the sigma from the population divided by the square root of n, which again was remembering the sample size. Okay, now it goes on to talk about, then this last sentence really isn't all that important, although you might see the phrase a little bit from the book. The standard deviation of the sampling distribution of X bar, or rather sigma X bar, is called the standard error of the mean. Again, that comes up a little bit later, not in stuff that we're going to get to though, so not to worry. Okay, a couple thought bubbles here. Underlying all of this is the fact that the sample must be a random sample. If you don't have a random sample, then all of this breaks down and it's all thrown out the window. So that's very important. Also, the sample values must be independent of each other. As we talked about back, oh my gosh, in a previous chapter, I can't remember what, but there was some chapter we talked about, we were talking about how if we saw the sample size is less than 5% of the population, then you could say your sample elements are independent of each other. So that the sample size was so much smaller than the population, you could pretty much assume that if you randomly picked from the population, you wouldn't get really people that were connected and therefore somehow dependent. Also, kind of an interesting side note, as the sample size increases, as n gets bigger, what happens to sigma of X bar? You can play around with that. If you just kind of make yourself a sigma, I mean, I'm literally just making that up out of thin air, and then find think about what happens when n is 10, what happens when n is 100, what happens when n is 1,000. And in each case, if you find sigma of X bar, you're going to see a pattern. What happens as n gets bigger. I will leave that exploration for you if you are interested. ... Now let's do number 2. Now again, the first sentence is going to sound identical to something we would have seen in chapter 7, and then it diverges a little bit. So let's start here. The length of human pregnancies is approximately normally distributed with a mean of 266 days and a standard deviation of 16 days. That again is the population. They are telling me that mu equals 266 and sigma is 16. And again, back in chapter 7, I might have given you that setup and asked you something like, what's the probability that a randomly selected human pregnancy goes more than 280 days? Or something like that, right? Well, we're going to answer similar questions, but not about actual human pregnancies, but about samples of size 20 human pregnancies. All right, so again, reading that sentence to make sure it gets read. A sample of 20 pregnancies is taken. That is to say n equals 20. Answer the following questions. Letter A says, what is the mean of the sampling distribution? And letter B asks for the standard deviation. Simply put, I am going to use my formulas. It tells me that mu of x bar is actually equal to mu. Again, really, I'm just picking that guy up there. And I was told the mu, or the population mean, was 266. I'm going to throw units on that. And that's my answer there. Like I said, no calculation needed. Now, for part B, I want to find the standard deviation of the sampling distribution of x bar, or sigma sub x bar. Again, my formula says that's going to be sigma divided by the square root of n. So, my sigma, again, is the population standard deviation. I was told that was 16. I'm going to divide it by the square root of 20. And it does tell me to round to the nearest hundredth, so that's 2 decimal places. I'm going to do that calculation, obviously, and come back with a number. Why don't you actually pause me down, make sure you can get the same number out as I do. All right, so I got 3.5777, blah, blah, blah. And so I rounded it to 3.58. Make sure you throw your units on that. And there we go. Now, what we now know, think about this. X bar is normally distributed with a mean of 266 days and a standard deviation of 3.58 days. Now let's go to the next page and use that information. So part C here, it says, since we can assume the sampling distribution to be normal, draw a normal curve with the mean and plus and minus 1 standard deviation mark. So here is my normal curve. Here is my mean at 266. I want to add 1 standard deviation here, and that will get me mu plus sigma, and then subtract sigma from mu and get down here. Go ahead and get those numbers back again. Remember, again, we are using the mean and standard deviation of x bar. So we got that. Go ahead, get those numbers out, and then, of course, if you'd like to answer D, I bet you'd be set up to do so. Go ahead and try that out. Okay, let's finish C and D up right here quick. I did 266 minus 3.58, and that got me that 262.42, which I put, of course, over there to the left of the mean. And then I did 266 plus 3.58, and that got me that 269.58. And, of course, I put it over there to the right of mean. So, in part D, it says, what is the probability that a sample of size 20 would yield a mean between 262.42 and 269.58? Which, of course, is exactly the 2 numbers that we came up with there. And so I'm talking about this area. And if you remember the empirical rule, then you know that that was 68%. So I'm going to say 68% of samples of size 20 will yield a mean between 262.42 and 269.58 days. All right. Why don't you pause me down, try to do E, and maybe even F, and come back when you're ready. All right, here's my work for letter E. So again, what is the probability that a random sample of 20 pregnancies has a mean gestation period of 260 days or less? So, of course, I drew a normal curve, and I have the mean, 266 there in the middle, and my 260 that I'm interested in is to the left of it. And then I want the area underneath the curve to the left of 260. And that's why I pulled up my normal CDF function in my calculator. And that, remember, we talked about in section 7.2, that is found by hitting the second key on the TI calculators and then the VARS key, which is under the arrows. And you'll see that the second function of that key is distra, or distributions. And so you pull up the normal CDF. Remember, it's CDF and not PDF. Then you put in the lower bound, the upper bound of the area that you're interested in, followed by the mean and the standard deviation, all separated by commas. And if you do that, you will get 0.047, which is to say, this area underneath the normal curve is 0.047, where the total area underneath the curve would be 1, right? So we say the probability that a sample of size 20 has a mean of 260 days or less is 0.047, or 4.7% of all of these samples of size 20 will yield a mean this low or lower. So that's good to know. About 5% of all samples will have a sample mean of 260 days or less. Now, I also want to talk a little bit about the lower limit that I put in there. Now, this is really, again, this normal curve is really just on the x-axis in an xy plane. And so what I did by putting 0 in there is, my scale is off, but I'm basically saying there's some 0 down here. It's really, really, really far to the left. And so I'm really finding that area. You need to put in a lower bound. The book might have you put in something like negative E99, which is basically a way of saying negative a gajillion, right? That's not necessary. All you really need to do is put in a value that is way, 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 way less than any pregnancy you're going to look at. 0 days means no pregnancy, right? So 0 works there. But you'll also see I could have put in 100 there and I would get out the exact same answer. The fact being, there's just not many pregnancies that are in this data, I should say, that have a gestation between 0 and 100 days. They're just not in that data. So I think you could even have put in 200, and you'll notice it gets you the same value out, because the amount of pregnancies between 0 and 200 days are very, 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 very tiny. And so they don't really kind of factor into it a lot. So that's how you deal with the lower bound that we need in this normal CDF. Of course, I found that area by the calculator, obviously, but you could have found a z-score and then looked that up in the paper table as we showed in 7.2 as well. That's just an alternative. And I'm sure I'm going to try to use that method a few times in the notes as well, just to give you practice with that. If you have not already, pause me down and try letter F. All right, so let's read the question. It says, what is the probability that a sample of size 20 would yield a mean gestation period within 5 days of the mean? Draw an appropriate normal curve with the area shaded. So again, I got the mean in the middle. I subtracted 5 days to get 261. I added 5 days to get 271. And again, it's that area inside there that I'm after. So I'm going to use the normal CDF. This time I have a lower bound of 261, an upper bound of 271, a mean of 266, and a standard deviation of 3.58. My calculator shot me out 0.837. So what we are saying is the probability a sample of size 20 yields a mean within 5 days of the mean, which is, remember, 266, is 0.837, or about 83.7% of all of those samples of size 20 will yield a mean within those two values. Now, do be aware, remember, the size 20 is important here. That 3.58 came from the formula of sigma divided by the square root of n. If we had a problem where they were asking about the probability that a sample of size 100 or 50 or some other number besides 20, we would have to redo the sigma and come up with a new value here, right? Because that sigma only applies for samples of size 20. Do be aware of that. All right, so let's see about non-normal populations. Now, again, it might seem self-evident or at least understandable that if a population is normally distributed, then we're going to say the sample means, or X bar, are normally distributed. That seems perfectly understandable, at least. Well, what about non-normal populations? And luckily, the answer is, yeah, usually they're normal too. So, not to worry. Let's read these couple paragraphs about that, and then we're going to test out our understanding on number 3 here. So I have the central limit theorem. It says, regardless of the shape of the underlying population, the sampling distribution of X bar becomes approximately normal as the sample size n increases. Okay, so from page 2, we know that if a population is normal, then X bar is also normal. And therefore, I can answer questions about the sample means using my chapter 7 stuff, right? That's what we've covered so far. Now here on page 4, we're saying, even if you know the population's not normal, you can say the sampling distribution of X bar is normal as long as your sample size is big enough. And of course the question would come up, well, how large does n have to be to make the sampling distribution approximately normal? It does depend on the population. If a population is very skewed, it tells me, then a larger sample size is needed. Well, that makes sense. A general rule of thumb is that if the population is non-normal or unknown, right, then a sample size of 30 is needed to ensure that the sampling distribution of X bar is approximately normal. Like this thought bubble says, the book really does do a really good job of showing that. Let's have you pause me down and try number 3. You're just going to test out the understanding of what I am saying up above. All right, so again, number 3 asks me, can I apply the methods of normal curves to these scenarios? In other words, are we justified in believing the sampling distribution of the sample mean is normal? So, in part A, it says household incomes are not normally distributed. That, again, is the population that they're referring to here. A sample of size 10, it tells me, is taken and the mean income is $75,000. So, the question is, could I then say to myself, what's the probability that I get a sample that the mean is more than 85,000? Can I answer that question with my chapter 7 stuff? Well, it turns out, no. I shouldn't use chapter 7 material to answer this question. And I wrote, the population is not normal Again, they tell me that in the first sentence. So we would need a sample size of at least 30. They tell me that up here for X bar to be normal. This sample size of 10 is not enough. All right. If you need to pause me down and think more about B and C, feel free and come on back when you're ready. All right, part B. It tells me the time in minutes spent in line waiting for the demon roller coaster is badly skewed to the right. If you've ever spent time waiting in line for a roller coaster, you know what they are talking about. It says a sample of size 50 is taken and the mean is 32 minutes. So can I assume that the sample mean X bar is normally distributed? In this case, I answered yes. And I wrote, although the population is non-normal, they're telling me that when they tell me that it's badly skewed to the right. I go on, the sample size of 50 should be enough to ensure the normality of X bar. And again, all I'm doing is saying, hey, even though the population is not normal, there would be enough wait times in the sample to say X bar is normally distributed. Again, if you haven't already, pause me down and try out number C. All right, letter C. The thicknesses of a type of metal fastener are normally distributed. A sample of size 15 is taken and the mean is 0.127 inches. So again, could I ask a question like, what's the probability that a sample of size 15 has a mean of 0.15 or more inches, right? Can I do that? And my answer is yes. The population is in fact normal. They tell us that there. So X bar will be normal regardless of the sample size. The point of part C is to recognize that if your population is normally distributed, you just don't need a size 30 sample. It's just not necessary, right? That central limit theorem and that size of 30 only has to do with if your population is not normal. Okay, let's discuss number 4 a little bit, and then I'll have you pause me down and try it out. So number 4, it tells me the most famous geyser in the world, Old Faithful in Yellowstone National Park, has a mean time between eruptions of 85 minutes. That will be our mu. It says then, if the interval of time between eruptions is normally distributed with a standard deviation of 21.25 minutes, answer the following questions. This 21.25 is our sigma. Now let me let's kind of break down that information. Let's think about Old Faithful throughout the day. And let's like say start at 6 a.m., right? And let's say it explodes at 6 a.m. There's the geyser erupting, okay? And then maybe it explodes again at 7 a.m. And there's the geyser erupting. It did not explode any time between those two times, right? And then let's say again, 7:45, and it erupts, right? And then maybe it waits until about 9 o'clock to erupt again. Maybe it's 10:30 when it erupts again, right? So what we're talking about is if you find the time between eruptions, this was 60 minutes. This was 45 minutes, right? This was, 75 minutes? That's 90 minutes, right? If you find the times between eruptions and average these numbers, you get 85 minutes, all right? If you find the standard deviation of these red numbers up here, you get 21.25 minutes. Now, full disclosure, I am making up these times up there, but I'm just trying to explain how they might have gotten a mean time of 85 and a standard deviation of 21.25 minutes. Okay? Not only that, but when you look at the interval of time between eruptions, which again are just these supposed red numbers up there, you will find they're normally distributed, which means again, there's an awful lot near the middle, near the mean, and as you get further from the mean in each direction, you get fewer and fewer times that would be there, right? So that's what we're trying to talk about. The time between eruptions. Now, in part A, they say, calculate the mean and standard deviation of the sample mean, but then it says assume a sample size of 30. What they mean to say is we are going to sample these red times. So of course, for several days, you'd have many of these times between eruptions, right? I want to randomly sample 30 of them. Maybe in that sample, I'll get that one and maybe this one and 28 other times between eruptions throughout the time period that they're studying. Okay, so that's what's going on. Now let's use our chapter 8 stuff to basically answer the chapter 7 questions, which is find the probability. So now part A here says calculate the mean and the standard deviation, and I'm talking about mu of x bar and sigma of x bar. So we've got a little bit of calculation to do there. And then part B will ask us a probability question. All right, so pause me down, do at least letter A and B. We will talk about C as it kind of has another implication down here as well. But pause me down and do A and B at least. All right, so I did part A. I calculated the mean, which was simply the mean of the population. And so I just didn't really do anything. I just wrote down 85 minutes. And then they were asking me for the standard deviation of the sample mean. And so that's sigma over square root of n. And again, sigma was that 21.25 from the population data. And I divided it by the square root of 30 because, again, it told me a sample size of 30. And I rounded that to 3.88. And I did attach the units minutes to that. Again, to interpret what the heck we've just done, I want you to picture taking these many, many times between eruptions, right? You've got many, many days of these numbers, and you're going to sample 30 of them. And for that one sample, I could average the numbers, right? And that would come up with the mean time between eruptions. That would be what I would call the sample mean, right? Okay, now, in theory, I could sample many, many times. So now I want you to picture many, many samples of size 30, each of them with their own sample mean. Well, it turns out, this is a little weird, but it turns out if we averaged all of those sample means, we'd get 85 minutes. And if we took the standard deviation of those sample means, we'd get 3.88 minutes. And because of what we've said previously, we know that this sample mean is normally distributed. And so in part B, I'm going to ask a probability question that has to do with the sample mean. What is the probability, it asks me, that a random sample of size 30 time intervals between eruptions has a mean longer than 95 minutes? This is the probability that my X bar is greater than 95. We are supposed to draw an appropriate normal curve and shade the area. Go ahead, pause me down, do that problem, maybe on the calculator. Maybe you change that 95 into a z-score and then look it up on that table we talked about in 7.2. In fact, I think probably I'll show both ways. Again, just pause me down, finish the problem, part B, the way you see fit, and then come on back. All right, so again, the question is asking me, what's the probability that I get a sample mean that's more than 95 minutes? And so I drew my normal curve down here with the sample means mu of 85 and then the 95 that I'm interested in, of course, to its right. And then I shaded the area underneath the curve to the right of that 95, because that would be where the eruptions, the time intervals between eruptions, have a mean longer than 95 minutes. So I decided to do it both ways. So I did it the 7.2 lookup table way. And so I needed to change my X score of 95 into a Z score so I could actually use the table. So Z equals X minus mu over sigma. Again, notice I'm using the mu and the sigma that I calculated in part A for the sample means. That gets me that the X score of 95 is equivalent to a Z score of 2.58. I looked that up on my normal curve table, which again is given to you in its entirety in the 7.2 notes, but of course is available through the book as well. Now, I look up 2.58 in the Z column. Really, technically, I looked at the 2.5 in the Z column, and then I went over to the column marked 0.08, and I found the area to the left underneath the curve is 0.9951, which again is that area is 0.9951. And since I wanted the other part, I needed to subtract it from 1, and so I did that. I ended up with the probability that a random sample of 30 time intervals between eruptions has a mean longer than 95 minutes is 0.0049. Okay, so here is me doing it on the calculator. Again, I'm using the normal CDF. I need to put in the lower bound, which is that 95, and then the upper bound. Again, the book will say put in E99 because that's an enormous number for the upper bound. You could. I did. And then followed by the mean, 85, and the standard deviation, 3.88. You do, in fact, get something that rounds to 0.0050, which you'll notice is ever so slightly different than the way the answer that we got from the standard normal table, simply because I think they round more in the standard normal table than the calculator has to round. So now, I would also like to point out, just like before, you can kind of play with that upper bound. I noticed that if I put 130 in there, it gave me the exact same answer. In fact, if I put 115 in there, it gave me the exact same answer. Only when I get to 100 that it starts to actually change the value of my my actual output. So again, E99 is just some crazy value all the way out here, right? And totally not to scale, right? So I'm just saying you could have used 130 and gotten exactly the same answer as you would have. So anyway, that is that one. Now, let's actually kind of write that, because this will help us with letter C. Let's write this, the probability that we ended up with, as a percentage. This probability is, in fact, let's see if I can find a place to write this. Turn a decimal into a percent means take the decimal place right, move it over 2 places, and then add on a percent sign. And that gives me 0.5%. 0.5%. So 0.5% is the probability that you sample 30 of these time intervals between eruptions and you get a mean longer than 95 minutes. So in part C, it's asking me, would I consider a sample mean that was longer than 95 minutes to be unusual? What that means is, if I were to have sampled 30 of these time intervals and gotten a mean of 95 or even bigger, would that be unusual? It all comes back to the basic definition of an unusual event, and I believe we saw it way back in 5.1 where we first saw probability. We were talking about unusual events being defined as those that have a probability that's less than 5%. Those would be unusual, right? And again, our probability here we found definitely less than 5%. In fact, it's 0.5%. So I'm going to say yes, a sample mean of 95 minutes is unusual. Now, what does an unusual result mean for us? That's actually something that leads us to chapters 9 and 10. But right now we'll say this. An event that is considered unusual should be looked at further. There are two possible conclusions. Number one, either the sample just happened to have high time intervals because after all, it is random, or, and this is usually the conclusion that we're going to go with, is that our assumption that the mean time is really 85 minutes is actually incorrect. So that's super neat. What we're doing is we're developing a way that chapters 9 and 10 will help us with of determining if in fact the mean time really is 85 minutes. That's a pretty cool technique that we see later in later chapters. So let's wrap up these notes in 8.1 here and now. Hopefully that gives you lots of good information as far as, how to do that homework, and keep those questions coming, of course. Bye.